Hello, my name is Ima Frank, your mathematics tutor. In this package, we are going to look at limits of functions of real variable. I want you to sit back with your book and your biro and then take down all the things that I'm going to teach you on limits. Thank you. Before we start, let's look at the behavioral objectives. At the end of this teaching, the students should be able to evaluate the limits of functions of real variable using the tubular approach or intuitive approach. The students should be able to evaluate the limits of function of real variable using substitution method, H method, expansion method. These are the objectives. Let's look at the definition of limits. But before we do that, I want to take you a little back to function of real variables. Now, let's look at definition. Let X be a non-empty subset of R. That is, X is a proper subset of R. A mapping F such that X mapped to R is called real valued function of real variable Now, in other words, I want to break here down what we really talk about, a mapping F such that elements are mapped from set X to R, that is the set of real number. What it means. So a mapping F such that elements are mapped from X to R is called real valued function of real variable. So in other words, a mapping whose domain and codomain consists of real numbers such that no elements in the domain is left without having an image, in the codomain and no elements in the domain has two images. In the codomain, but two elements can have one image. In the codomain is known as a real valued function of real variable. All right, so this is the definition of function of real variables. Let X be a non-empty subset of R. That is, X is a proper subset of R. A mapping F such that X is mapped to R, that is, elements from X are mapped to R, is called real valued function of real variable. So in other words, a mapping whose domain and codomain consists of real numbers such that no element in the domain is left without having an image in the codomain, and no element in the domain has two images in the codomain. That is, one single element cannot have two images in the codomain, but two elements, or let me say at least two elements, can have one image in the codomain. All right? In the codomain is known as real valued function of real variables. Now, I want to review a little about mapping. And I believe you have had an idea about mapping. If you are not, then there is a lecture delivered on mapping, which you can really get proper understanding of mapping. But let me just review what it means. Let us consider these two sets. Consider the two non-empty sets below. Set X is, we have -2, -1, 0, 1, and 2. We have another one, set Y, which is 2, 5, 1. Okay. These are two sets. Now, I want to put it in a diagram called arrow diagram so that we can then see the mapping and know what we mean by function. This is arrow diagram. Now, this is set X, this one, and this is set Y. There is a rule F that assigns values element from here to here. Now, this place is called the domain. This one is the codomain. Now, element of set X is -2, -1, 0, 1, and 2. This is the elements for set X. Then for set Y, we have 2, 5, and 1. Now, there is a rule that assigns these values. Okay. We are going to discover the rule that assign that direct this arrow. But from what we define here, you see that no element is left in the domain without being assigned to image, and no one element, that is one element, any one, a particular one, will have two images. So, and then you see that the domain and the codomain are made up of, that is, they consist of ray numbers. Array number. So this is a mapping which results in function of real variables. Okay, let us explain some things here. I have something like this, y equal s squared plus 1. I want to show us that the arrow is directed by a rule called x squared plus 1. Now look at it. If x, for the x-axis, for the x set, for the set x, for the first element there is minus 2. So minus 2 squared plus 1 will give me 4 plus 1, which is 5. You now see minus 2 is directed, the arrow is directed to 5. Now, so it means that when x is minus 2, y is 5. So when x is minus 2, y is 5. All right. Now, when x equal minus 1, we have that y will be equal minus 1 square plus 1, which is 1 plus 1, and it gives us 2. So at x equal minus 1, the arrow directs to 2. Then when x equal 0, we have y will be equal 0 squared plus 1, that is putting 0 in the place of x, and that will give us 1, and that is why you see 0 is directed to 1. Right. When x equal 1, so we have y1 squared plus 1, which is 1 plus 1, and is 2. So we now see that at 1, the arrow is directed to 2. So again, when x equal 2, we have that y equal 2 squared plus 1, which gives us 4 plus 1, which is 5. Notice how 2 is directed to 5. So you now see that the value of y depends on the value of x. The value of y depends on the value of x. When x was minus 2, y is 5. When x is minus 1, y is 2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 5. So y does not have its own say. It is only what x gives y that y become. So that we can write it this way. That y is depending, or y depends. Let's do this. Y depends on x. Yes, truly, we have seen it that y depends on x. That means the value of y depends on the value of x. Now here, x does not depend on y because it is x that gives before y has a value. So we then call y dependent variable because it depends on x. We then call x independent variable. Now, we wanted to, I'm trying to see how I can show you what function really means. Now, if we write like this, y equal x squared plus 1. Look at, this is a function where the dependent variable is y, independent variable is x. So the value of y is generated by the rule. The rule is x squared plus 1 that generates the value of y in the codomain. So this word here, y depend on x. In mathematics, we will say that y is a function of x. So the word function here, you can see correspond to here. Things that depend. Do you also know that 70% of students, they are functions? How? Because they depend on their parents, they depend on their uncles for their school fee and other things. So the parents here, the parent is independent variable, while the student is dependent variable. So the student is a function of the parents. That is how function works. So here we can see that we have functions here, and this function is function of real variable, because you are talking about numbers here. We are talking about real numbers. Okay, so that is what we call function of real variables. Now we are going to look at limits of function of real variable, and we'll look at limits and continuity. But we'll start with limits, and before we talk about continuity. You know, when you depend on somebody, there must be a limit of dependence. So that is what we want to look at now, what limits really mean in terms of function. We are going to look at limits and continuity of function of real variable. But before that, we'll start with limits. Definition of limit. If x approaches a number c as f of x approaches a number L, the L is called the limit of the function f of x. Mathematically, we write lim f of x as x approaches c equal L. All right. So now this definition will be illustrated for proper understanding using table. Now, consider the function. Let us take the function, the one we just finished, that we generated from two sets. Consider the function f of x equal x squared plus 1. You know, the function there, we wrote it y equal x squared plus 1. Is the same thing as writing f of x, because y equal f of x. So you can write f of x equal x squared plus 1. All right. And consider the function f of x equal x squared plus 1 as x approaches 2. The tables, we have two tables now. The tables below illustrate the concepts. The concepts of limit for the above function as x approaches 2. Now look at that. This symbol means approach. X approaches 2. We'll use two tables. This is x and this is f of x equal x squared plus 1. We also have another table for x, and f of x equal x squared plus 1. Good. And I want to also take us to the Cartesian plane. I'll use the Cartesian plane to also illustrate this fact. This is the y-axis, this is the x-axis. Now here is the origin. We have here 1, we have 2, we have 3, and so on. Here we have 2, 4, 6 in the y-axis. So what happened is that we want to see how x, this is x-axis, how the values of x will approach 2. Now this place is 1.5 because this is 1, this is 2, so this is 1.5. In this table, I'm going to use it to demonstrate this concept, the concept of this particular one. This one is when x approaches 2 from the left hand side, we'll take the value of x very, very close to 2. We are not interested in 2 at 2 proper, but we want to see the behavior of f of x when x approach 2 from the left. Then later we'll also look at the behavior of f of x when x approaches 2 from the right. And we have a notation when it approaches from the left and from the right, which I'm going to show you. So here, when x is at 1.5, you know we have here 1.5. There's another one here, 1.6, 1.7, 1.8, 1.9, 1.99. 1.9999 is very close to 2, but it's not 2. So now here, if x is 1.5, what will be the value of f of x? We are going to substitute 1.5 here plus 1. So if you do that, you have 1.5 squared plus 1 will give us 3.25. Now at 1.6, we'll have 1.6 squared plus 1. This will give us 3.56. At 1.7, then we'll have 1.7 squared plus 1. So this gives us 3.89. At 1.8, we'll have 1.8 squared plus 1 will give us 4.24. Then 1.9, we'll look at 1.99. We'll look at 1.999. These are the places we'll look at. So at 1.9, we have 1.9 squared plus 1. Give us 4.61. So at 1.99 squared plus 1, we have 4.9601. Then 1.999 square plus 1 give us 4.996001. All right. So you see, what we mean is this. What we mean is this. At 1.5, look at that. At 1.5, value of x, f of x has 3.25. Okay, this is 3, the middle here. So 3.25, assuming is somewhere here. Now this place here is 5. So when x is 1.6, we have 3.5. When x is 1.7, 3.89, very close to 4. When x is 1.7, sorry. When x is 1.8, we have 4 points. Look at that, 1.24. When x is 1.9, we have 4.61. When x is 1.99, very close to 2, we have 4.9601. When x is 1.999, we have another one here, which is 1.996,001. Now you see, as x approaches 2, the value of f of x approaches 5. See, it's coming up to 5. Now, here, x approaches 2 from the left. We write this sign to mean it is from the left. It's approaching 2 from the left. Why f of x, look at that, approaches 5. When x approaches 2 from the left, f of x approaches 5. Look at, it started from here. When we say 1.5, f of x was here. 1.6, f of x was, so the thing is moving till where we say limits. You know, why do we call here limit? Because if I say 1.999999 any number of times squared plus 1, it cannot pass 5. Try it and see. For your calculator, 1.999999 any number of times that you like, square it plus 1, it can't pass 5. So that shows that the limit of this function as x approaches 2 is 5. Okay, it does not just finish there. We want to also see what about when x approaches 2 from the right, because if you call somebody and the person say, I'm approaching so place, you don't know whether it's approaching from the left of that place or from the right. So you see how interesting mathematics is. It takes all those things into consideration to see when it approaches from the left and also from the right. Okay, let us consider this table when x approaches 2 from the right. And here I want to use another plane. I'm going to use another plane to demonstrate that. This is 0, 1, 2, 3, and it goes on the x-axis. So this is 2, 4, 6. 6. This is the y-axis. Okay, so when x approaches 2 from the right, I want to start here, which is 2.5. You know, why I like starting from middle here is, even though I start here, I will still come to this place. So to save time, I want to start here and move to this side. So this side, this place is 2.4, 2.3, 2.2, 2.1, then 2.01, 2.001 is very, very close to 2. We'll take it very close to see the behavior of f of x. Right, so in that place, when x is 2.5, x is 2.5, it's coming from the other way. So if I put it here, 2.5 square plus 1, you give me 7.25. Now 2.4, 2.3, 2.2, 2.1, 2.01, 2.001, 2.0001. Right, very, very close to 2. So here, when it is 2.4 square plus 1, we have 6.76. Now, at 2.3 square plus 1, we have 6.29. Then 2.2 square plus 1 will give us 5.84. 2.1 square plus 1 will give us 5.41. Then 2.01 square plus 1 will give us 5.0401. Then this one is 2.001 square plus 1 give us 5.004001. So this is 5.0004001. Now notice that. So here x approaches to plus. We use plus here to see that it's coming from the right hand side. And we can see that this one, f of x, approaches 5. That is what f of x does. It approaches 5. So now, because if you approximate this, it's 5. Let us see the diagram here. Let us see it here. When x is 2.5, we have 7 points. The next place here should be 8. So somewhere here we have 7 there. Okay. So somewhere here we have 5 at the middle of this. Okay. So when x is 2.5, we have 7. So the thing becomes this way. 7.25. Go this way. Then when x is 2.4, you have 6.7. So somewhere here. Now when x is 2.3, you have 6.29. So you can see it reduces to here. When x is 2.2, you have 5.89, close to 6. When x is 2.1, we have what? 5.41. 5.41. So when x is 2.01, very close to 2, we have another one somewhere here. When it is 2.001, it's 5.0. When it is 2.0001, we have, look at that, we have 5.0004. So what do you also see from this particular diagram? You see, it also comes from the other side. This diagram here, in this one that was coming from the left, it was coming from down and approaches 5. So here now, it's coming from up and approaches, and it stopped at 5. Now, if you see 2.000000, as you like, 1 square plus, very, very close to 2, the highest number you will get is 5. So that tells you that this 5 is what we call the limits. And you see, from the left, from the right, the limit is 5. Now, let us go now back to the definition so that we will now understand what the definition is talking about. If x approaches a number c, now in this context, c is 2. If x approaches a number c, now the c is generalization because it can approach another number, it must not be 2. So we will not say if x approaches a number 2, no. But if x approaches a number c, that is c stands for any number, as f of x approaches a number L, in this context, f of x approaches a number 5. The L is called the limit of the function. So in this context, this 5 now is called the limit of the function. All right. So But there is something I want to do again. I want to also look at this function and find f of 2. So I know that f of x equal x squared plus 1. Now what about f of 2? F of 2 is 2 here square plus 1. And that gives me 4 plus 1, which is 5. Good. Now, I'm going to list out the 3 properties I've seen in this function. The 3 limit properties I've seen. In this function, we have seen, number 1 property is that 1, lim f of x as x approaches 2 exists. That is number 1. We have been able to find the limit. Look at this here, 5. Number 2 is that lim f of x as x approaches 2 is equal f of 2. No, look at it. The limit of f of x as x approaches 2 is 5. And then f of 2 is also 5. Okay. Another property again I see is that the limit of f of x as x approaches 2 negative, that is from the left, is also equal to the limit of f of x as x approaches 2 from the right. Now, this property number 3 implies that f of 2 exists. That is what it means. F of 2 exists. As I put f of 2, it exists. Okay, we are going to take other functions so that we'll also see those ones that are not having these properties. You see, this property is very important because when we are going to talk about continuity, you'll be able to know functions that are continuous even when you are looking at it. You know, the ones that are continuous. So that is the area we are going. Now, I'm going to still look at limits using another function. Thank you. Let us take another function and examine the limits. How f of x behave when x approaches a particular number. We consider this function. The function f of x equal x squared minus 1 over x minus 1. Now, we want to evaluate the limits as x approaches 1. That is, we evaluate lim x squared minus 1, x approaches 1. Lim x squared minus 1 over x minus 1 as x approaches 1. What will be the limits? I would like us to use the tabular approach again so that we can see it clearly. Then after this, we'll use various methods of limits. But I want you to really understand the concepts of limits. All right. So, using table again, I will have 2 tables. This one is for x, then f of x. F of x equal x squared minus 1 over x minus 1. I have another one here, table 2. The same thing here, f of x equal x squared minus 1 over x minus 1. And this is values of x. Remember, we use this when x approaches 1 from the left. Then this table will give us the values when x approaches 1 from the right. Now, we'll also use the Cartesian plane to see the picture. This is 1. This is 1. This is 2. And we'll have something like this. 1, 2, 3, 4. This is the y-axis, and this is the x-axis. So when x approaches 1 from the left, we'll start somewhere here, which is 0.5. Of course, there will be 0.6, 0.7, 0.8, 0.9, 0.99, 0.999 we get to 1. Same will also apply in the other way, just as we did the other time. Okay, when x is 0.5, we are going to put 0.5, 0.5 square minus 1 will give us minus 0.75, then divided by 0.5 divided by minus 0.5. You know 0.5 will be downside. So 0.5 minus 1 is minus 0.5. So it will give us minus 1.5. It will give us 1.5. Now, when x is 0.6, that's when x move from here to here. Then we'll have 0.6 square minus 1. Okay. Divided by 0.4. Divided by minus 0.4. So it will give us 1.6. Now when s is 0.7, we have 0.7 square minus 1 divided by minus 0.3. That gives us 1.7. So when x is 0.8, from this approach we know that is 1.8. Then 0.9 give us 1.9. 1.9. Okay. Then what about 0.99? 0.99. Now in that place we see that 0.99 square minus 1 give us minus 0.199. Okay, minus 0.0199. All right, so we then have 0.99 minus 1. This gives us minus 0.01. So if we see 0.0199 divided by 0.01, we have 1.99. So meaning that 0.999 will give us 1.999. Okay, very close to 2. We have taken it very, very close to 2. So here, x approaches 1 from the left side. And then we see that f of x approaches 2. When x approaches 1, f of x approaches 2. Now let's do that using the coordinate plane. At here, 0.5, f of x was 1.5. That's somewhere here. Then when we get here, f of x become 1.6. When we go here, f of x 1.7. When we go here, f of x become 1.8. The next one, f of x become 1.9. The next one here, 1.99. f of x very close to 2. You see that? So it now landed very, very close to 2. So it's approaching 2. All right. It's approaching 2. You see how where it starts and it's going up, up, up and approach 2. Now, if we say 1.999999, anyhow we want to take it very close to 2. And then you see that the value of f of x cannot exceed these two. That is when it is approaching x from the left. Now let us look at this diagram also, talking about the Cartesian plane. This is 1, this is 2. This time f of x will approach 1 from the left. So you have things like this: 1.4, 1.3, 1.2, that is 1.2, 1.1, before very close to 1. This is 1, while this is 2. Okay. Now, in this one, we also have 1, 2, 3. So this is y-axis. So when x is 1.5, that is from here now, it's coming this way, it's approaching 1. When x is 1.5, we have something of this nature. We have a 1.5 square minus 1 give us 1.25. Now 1.5 minus 1 gives us 0.5. So meaning that 1.25 will divide by 0.5, we'll have 2.5. 2.5. That is somewhere here. This is 2, this is 2.5 before 3. So you see that here, and then we have 2.5. When x is 1.4, that is coming down to this way. Let's see. 1.4 square minus 1 is 0.96. Then the downside, if you see 1.4 minus 1, we have 0.4. Now 96 divided by 0.4 give us 2.4. 2.4. Okay. Now 1.3, 1.2, 1.1, 1.01, 1.001. Then we have 1.0001. We are taking it very close to 1. Then 1.3 square minus 1 give us 0.69. 0.69. Then 1.3 minus 1 give us 0.3. So if you say 0.69 divided by 0.3, we have 2.3. 2.3. So from look of things, this one will be 2. This one will be 2.2. This one will be 2.1. Then we come to here, where we will have 2.01. Here will be 2.001. Let's confirm that. 2.01 square. Yes, minus 1. 2.01 square minus 1. 2.01 square minus 1. The upside there is giving us 3.0401. Then the downside is 1 point, this place, 1.01. 1.01 square minus 1 is giving us 0.0201. Then the downside, if you go 1.01 minus 1, it give you 0.01. Now 0.0201 divided by 0.01 give you 2.01. All right, so this is 2.02 and this is 2.0001. Now what it means here, as we have seen, is that as x approaches 1 from the positive side, then f of x approaches the number 2. Yes, because here, if I approximate it, it will be 2. Now let's look at the diagram too. At 1.4, we have 2.4, somewhere here. At 1.3, also have 2.3. At 1.3, you have 2.3. Okay. At 1.2, you have 2 points. Okay, this is 1.2. So we have 2.2. At 1.1, we have 2.1. At 1.01, you have here 2.01. So what we are interested here is the approach. Now see, when x is approaching 1 from the right hand side, you can see the value of f of x start from up and approach and come down. Start from here and be coming down to 2. These 2 is called the limit. Now notice that in this one that was left, the value of x started from here and go up. That's from 1.5 and go up. So these 2, this particular 2, is where we say it has the limit. Now I want us to also bring out the properties again, things that we can detect quickly in this demonstration. Is that if I find f of 1, for instance, f of 1 will give me 1 square minus 1 over 1 minus 1. And this gives me 1 minus 1 over 1 minus 1, which is 0 over 0. Of course, this is 0 over 0. All right. So, meaning that this is undefined. So I see that f of 1 is not defined. It's not defined. So I now notice these properties. Property number 1 is 1 is that lim f of x, the limit of f of x as x approaches 1 exists. Yes, exists, which is 2. We have seen the limits. Rule number 2 is that lim f of x as x approaches 1 is not equal to f of 1, because f of 1 give me 0 over 0. The limit of f of x give me 2. So it's not equal f of 1. Number 3 is that f of 1 is not defined. Another word there is that f of 1 does not exist. F of 1 does not exist. So these are the properties that I've seen here. These properties are very important when we are going to talk about continuity. So you have to note them. Property number 1, we say the limit of f of x exists. What does that mean? It means that we have seen the limits, because from this table, this table, the limit here is 2. If you come this way, as x approaches 1 is also 2, so the limit exists. Now we come to find f of 1. You see that f of 1 has that value 0 over 0, which is undefined. So meaning that limit of f of s is not equal f of 1. In the first one that we did, limit of f of s was 5, and then f of 2, which is the value that x was approaching, was also 5. So we say that the limit of f of x equal f of 2. Good. Now another thing is that f of 1 is not defined, because what it gave us there is undefined expression. Right. We are going to take one more on this limit before we now look at other methods that we can evaluate limits of functions. We are going to look at another function. We are going to consider another function and look at the limits as x approaches a number. And look at this. We consider this one. The function f of x equal x. Evaluate its limit as x approaches 3. This function, this sort of function is called greatest integer function. In a particular lecture where I render a lecture on mappings and functions, we look at different types of functions. So if you have such lectures, you hear about greatest integer function. This is not the absolute value function. The absolute value function is different, as is written in this way. The absolute value function. This is the greatest integer function, and it has one behavior. The greatest integer function is that if I write the negative, the decimal, if it has decimal number, like it has something like 1.5, then it will be equal to 1. 1.4 will be equal to 1. I will only take the whole number parts. The whole number parts. So that is one of the behavior of the greatest integer function. And so we are going to use table again to also see. I like to use table. After this, we use another method. But you see that the tabular method will help you to see the picture of limit, what it means. This is x, and this is f of x. F of x is equal x. All right. And this is another one, another table for values of x and values of f of x. Good. So, want to look at it as x approaches 3. First, like to draw the Cartesian plane that will help us to demonstrate these concepts. So here we have 1, 2, 3, then this is 4. Then this one will give us 1, 2, 3, 4. This is the y-axis, and this is the x-axis. So I start from here, 2.5, to approach 3. This is 2.5, 2.6, 2.7, 2.8, 2.9, and that is here when x approaches 3 from the left. So here 2.5, when x is 2.5, f of x is 2. How? Because if you put 2.5 here, we take the whole part, which is 2. When x is 2.6, that is, x has moved from 2.5 to 2.6. And f of x is 2. When x is 2.7, f of x is 2. 2.8, f of x is 2. 2.9, f of x is 2. 2.99, f of x is 2. 2.999, f of x is 2. So here, x approaches 3 from the left, and then f of x equal 2. F of x is 2. Okay, we'll go this side, as this table, for values of f of x. Okay, before then, let us see what this means. It means that at 2.5, I have value here, 2. At 2.6, it is still 2. 2.7 is 2. 2.8 is 2. 2.9 is 2. 2.99 is 2. So we put a line like this. Look at how that one is. That's how it is. So that is a graph of greatest integer function. It is like a staircase. If I plot the graph of greatest integer function, if you look at this graph, it's like staircase. So what I'm saying there is that the whole value from here to here fall at one place. Let us go for the one that f of s is also coming from the right hand side. This is 0, 1, 2, 3, 4. And since x is approaching 3, This is 1, 2, 3, 4. From the right, we will have 3.5 here. So the next one is 3.4, 3.3, 3.2, 3.1, 3.01, very close to 3. And we'll have something like this. 3.5 give us 3, 3.4, 3, 3.3, 3, 3.2, 3, 3.1, 3, 3.01 give us 3, 3.001 give us 3, 3.0001 still give us 3. So when x approaches 3 from the right, see the positive sign from the right, then f of x is 3. We see one property again here very quickly, that when x approaches 3 from the left, f of x is 2. When x approaches 3 from the right, f of x is 3. And from the previous ones we have done, you see that the two tables, they were having the same limits. They were having the same, but this one does not have the same. Okay, so if we want to also look at the graph of this, we see that at 3.1, yes, 3.01, we still have 3. That is here. The whole of this piece, 3.1, 3.2, 3.3 is all here. That means if I want to draw it here, look at how this one will be at this particular place. Let me put the two in one diagram, in one Cartesian plane. 3 is somewhere here. It takes here from 3.5. So you see the staircase, it has staircase. If I want to consider from 1 between 2 to 1, between 1 and 2, I will have another staircase here. I have another line here which shows a staircase. So that is how these functions behave. Then I now want to list the properties, what I have seen there. I have seen that lim f of x as x approaches 1, no, as x approaches 3, yes, as x approaches 3, exists. No, does not exist. How? Because I've not got one side. I've not got, well, this one is giving me another one, this one is giving me. So does not exist. Then that is number 1. Number 2, lim f of x as x approaches 3. Yes, if I say f of 3, what will I get there? F of 3 will give me 3. But this lim is not equal f of 3 because the other one is not giving me one issue. So it does not allow the limit to exist. Another thing is that, yes, f of 3 exists. If I talk about f of 3, putting the value, it exists. So you see that this one is a different thing entirely from the other properties that we had. Please take note of this because I'm going to use it to define continuity. That is why I take time to bring the properties. All right, so now we want to look at other methods of evaluating limits because there are so many methods, but we are going to look at some of them now, and then we compare it to what we are doing now, and then you see that this tabular approach, also known as intuitive approach, really show the picture of limits. That's what we want to do now. We are going to look at different methods of evaluating limits. We start with substitution method. In this method, we substitute the value in which x is approaching directly into the given function. Example, evaluate lim x squared plus 1 as x approaches 2. Alright, so this is the first one that we did using tabular method. So this is what we will do. Lim x squared plus 1 as x approaches 2. So we substitute x equal to into the function. We'll have 2 squared plus 1, which is 5. And this was the limit that we had when we used tabular approach. But you see, assuming you did not know about the tabular approach, look at this, you did not know about the tabular approach. You only know substitution approach. And then you said, when you have a function, you want to take the limit, you substitute it. How will you understand the concepts of limits? Will you even know what it means by x approaching a number from the left and from the right? You won't. By this, you won't know. So that is one advantage of the tabular approach. It shows you how the value of x approaches a number from the left and from the right, and how f of x behaves. So that is the substitution approach. Let us take another one, and which is the second one that we did. The second one that we did using tabular approach. I'm going to evaluate lim x squared minus 1 over x minus 1 as x approaches 1. So this is the solution. Lim x approaches 1, x squared minus 1 over x minus 1. So I'm going to substitute x equal 1. Then I will have 1 squared minus 1 over 1 minus 1. This gives me 1 minus 1 over 1 minus 1. And that is 0 over 0. Now, in this type, to get the limit, we factorize f of x. Factorizing f of x, we have x minus 1, x plus 1. You know, this is different of 2 square, because 1 square is still 1. So we can write this upside as this over x minus 1, where x minus 1 cancel x minus 1, remain x plus 1. So now substitute x equal 1. So here we'll have 1 plus 1, which is 2. Now this is the limit. And in that tabular approach, if you go back to your book, what you have written, because I told you from the start that you should write everything down. So as you go back and examine this function when we're using tabular approach, you see the limit was 2. So that is the substitution method. We are going to take one example about substitution method. Evaluate lim 4 minus s squared over 3 minus s squared plus 5 as x approaches 2. As x approaches 2. Okay, so notice that what we are doing is substitution method. So lim 4 minus s squared as x approaches to over 3 minus root x squared plus 5, x squared plus 5. Now substitute x equal to, then we have 4 minus 2 square over 3 minus 2 square plus 5. That will give us 4 minus 4 over 3 minus 9, because here will be 4. 4 plus 5 is 9, which is the same as 4 minus 4 over 3 minus 3. Square root of 3 is 9. So that gives us 0 over 0. Now, in this type that involves radical, we are going to rationalize just the same way we did in sort, rationalization of sort. So, rationalizing, we have 4 minus x squared over 3 minus root x squared plus 5 times, look at that, 3 plus root x squared plus 5 over 3 plus root x squared plus 5. So that is how we rationalize, by taking the conjugates of this. If we do that, we have 4 minus x squared, 3 plus root x squared plus 5, that is multiplying the up. If you go here, you have 9, that is this 3 times 3 is 9. 3 times this will give us plus 3 root x squared plus 5 minus 3 root x squared plus 5. That is this times this is 9. 3 times this plus root x squared plus 5. And this times this is minus 3 root x squared plus 5. So what remains now is this particular radical multiplying this radical. But here I carry minus. So we have minus x squared plus 5. You know how? Because when a radical multiply radical, that is square root times square root, the answer is the quantity inside the square root. For instance, root 2 times root 2 will give you root 4, which is 2. Root 3 times root 3 will give you root 9, which is 3. Always the answer, the quantity inside the square root. So that is what we have here. And this will give us 4 minus x squared, 3 plus root x squared plus 5 over, of course, this will cancel. I will cancel, so we have 9 minus x squared minus 5. Yes, which give us 4 minus x squared, 3 plus x squared plus 5 over 4 minus x squared. You know how? 9 minus 5 is 4. So we see that these can cancel this, and we come to have 3 plus root x squared plus 5. So now substituting x equal to, we then have 3 plus 2 square plus 5. So that gives us 3 plus root 9, which is equal 3 plus 3, and that is 6. So the limit is 6. All right. This is where we will stop for substitution method and also look at other methods. We are going to look at the H method of evaluating limits. In this method, we replace a plus h in place of x. Then by simplifying h and h approaching 0, we have the limit of f of x. So this method specifically works when you want to evaluate functions that by direct substitution it will give you undefined expression. For instance, look at this example. Evaluate lim x cubed minus 1 over x minus 1 as x approaches 1. So in this one, a is that value that if you substitute, you give you undefined expression. So that is always a. So here, we'll take the solution in this way. I have lim x approaches 1, x cubed minus 1 over x minus 1. So I will now say, I now replace 1 plus h in place of x. You know why? Because if I put 1 direct, I've seen that if I put 1 here and 1 here, that it will give me undefined expression. So that is what we call a. So a in this context is 1. So I will just do that by saying, now 1 plus h cubed minus 1 over 1 plus h minus 1. By expansion, I will have 1 plus 3h square plus 3h. Okay, look at that. 1 plus 3h square. Then this will be 1 plus 3. This is 1 cube. By binomial expansion, 1 cube plus 3. 1 will give you square. Okay. H will be 1 plus 3. H will be 2. Y 1 is 1 plus the next one is h cubed over, this is binomial expansion. If you know binomial expansion, or you can watch our lectures on algebra and trigonometry. You get to where we talk about binomial expansion. You can see the properties there and you can expand. Even though it's raised to power 20, you don't have problem of it. So this is the expansion of this. Now, the downside gives us 1 plus h minus 1. Then we see that 1 minus 1 can go. So we have 3h plus 3h squared plus h cubed over h. Now, I'm going to divide. Dividing through by h. I'm going to divide through by h, not by the highest power of h. No, we are not doing limit at infinity yet. So we'll divide through by h. This is cube. So we'll have 3. We are dividing numerator and denominator. So you have 3 plus 3h plus h squared over 1. Because if you divide here, it gives you 1. Then, as h approaches 0, we have 3 plus 3 times 0 plus 0 square, and that gives us 3. So the limits now become 3. So that is the h method of evaluating limits. We'll take another example. So we want to take another example on h method. Evaluate limits as x approaches 5 of x squared minus 25 over x minus 5. Leave x squared minus 25 x minus 5 as x approaches 5. So here we substitute. We substitute 5 plus h. It's x is approaching 5. But if I substitute 5 here, it will give me undefined expression. So I have to substitute 5 plus h into f of x, into the function f of x. So we'll have 5 plus h squared minus 25 over 5 plus h minus 5. Then this will give me 25 plus 10h plus h squared minus 25 over h. By binomial expansion. By binomial expansion, you have this. 5 plus h squared means 5 plus h times 5 plus h. If you expand it, you have this. So this can go with this. And so we have 10h plus h squared over h. So now we are going to divide numerator and denominator by h. Then we'll have 10h divided by h plus h squared divided by h over h divided by h, which gives 10 plus h. Yes, over 1, which is 10 plus h. So as h approaches 0, we have 10 plus 0, which is 10. So this becomes the limits. The limit there is 10. All right. So we'll look at another method known as expansion method. Now we are looking at another method called expansion method of evaluating limits. This method only works for functions which can be expanded in series. Now, consider the series expansion. Consider the series expansion of the following functions. Exponential x, exponential minus x, sine x, cos x, 1 plus x raised to n. Now, these functions can be expanded in series. So, it is also I assume you know the expansion, the series expansion of these functions. If you don't know, in algebra and trigonometry, I have delivered lectures on expansion of functions, like the sine function, the exponential function. You see it there, their series expansion. under complex number. At the end part of it, you see where I have taught this. But let me just show you the expansion of exponential x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x raised to the power 4 over 4 factorial. Now, this is the series expansion of exponential x. Then, exponential minus x is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x raised to the power 4 over 4 factorial minus, and it continues in this way. This is the expansion of exponential minus x. And for sine x, for instance, sine x, we have x minus x squared over 2 factorial plus, minus x cubed over 3 factorial plus x raised to the power 5 over 5 factorial minus x raised to the power 7 over 7 factorial plus, this is the series expansion of sine. Then for cos, we have 1 minus x squared over 2 factorial plus x raised to the power 4 over 4 factorial minus x raised to the power 6 over 6 factorial plus, and so on. This is the series expansion of cos. Then for 1 plus x raised to n, we have 1 plus nx plus n minus 1 over 2 factorial. Then we have x raised to 2 plus n minus 1, n minus 2 over 3 factorial. Then x raised to the power 3 plus, and so on, provided absolute value of x is less than 1. Okay, now for any positive n, the series is finite. You know, what we are doing here is infinite, that is continuous. But if n is positive, of course, it will have finite terms. You can see that in binomial expansion, algebra and trigonometry. I've done lectures on that. So now, knowing this expansion will help us to use it and evaluate limits. So let us see how we can apply it to evaluate the limits of functions. Now, example, show that lim x approaches 0 of sine x over x equal 1. I want to show that if you take the limit of sine x over x is equal 1. You know, we have said that this particular method will only work for functions that can be expanded by series expansion. So I have the solution in this form. I know that the limit of sine x over x as x approaches 0 is equal the limit as x approaches 0 of sine x. Then sine x is x minus x cubed over 3 factorial plus x raised to the power 5 over 5 factorial minus x raised to the power 7 over 7 factorial, continue in that way, over h. Look at that. So I've been able to express sine in the series expansion. So the next thing I will do there is to divide. Dividing through by x, I'm going to divide numerator and denominator by x. That will give me lim x approaches 0, x divided by x minus x cubed over 3 over x 3 factorial, because if you divide here over x, it's the same thing as saying 3 factorial x plus x raised to the power 5 factorial x plus, okay, minus x raised to the power 7 factorial x over 1. You know, I'll divide this by x to become 1, and that gives me lim x approaches 0 of 1 minus, so this will be x over 3 factorial, that is x squared over 3 factorial, because this x cancel x here. Then this one is plus x raised to the power 4 over 5 factorial minus x raised to the power 6 over 7 factorial plus, and so on. So as x approaches 0, we have 1 minus lim x approaches 0, 1, then we have 0 square over 3 factorial plus 0 raised to the power 4 over 5 factorial minus 0 raised to the power 6 over 7 factorial plus, and so on. Then everything here becomes 0. So we have lim x approaches 0 of 1, which is equal 1. So we have been able to show that the limit of sine x over x as x approaches 0 is 1. Now, this is expansion method of showing it. Now, there are other methods that we can use, like the L'Hopital rule, which we are going to see in application to differentiation. After we finish this, it is assumed here that you have not studied differentiation, even when you know. All right, so in application, you see the L'Hopital rule can be applied to this kind of problem. Now, let us look at another example. We're going to evaluate lim as x approaches 0 of exponential x minus x over x. All right, so we see that these are functions that can be expanded by a series method. So we can write this lim x approaches 0 exponential x minus exponential minus x over x. You can write it as the limit as x approaches 0. Then exponential x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, continue in that way till we have minus, then here again 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus, you continue in this way. Okay, so over x, and that will give us the limiting value as x approaches 0 of 1 plus x square over 2 factorial plus x cube over 3 factorial plus, then this minus can open here. We have minus 1 plus x, then we have minus x square over 2 factorial plus x cube over 3 factorial minus, so over x, right? So this gives us, now this one can go. We have here x plus x, we have 2x, then this and this can go, then this will give us plus 2x cubed over 3 factorial over x. You know this x square over 2 factorial, and this can go because this is minus, this is plus. So this plus this give us 2x cubed over 3 factorial. Right, so dividing numerator and denominator. By x, we have the limiting value as x approaches 0 of 2x plus 2x squared over 3 factorial. Now notice that when x divide, okay, when we divide here, so this one remains x squared. Of course, this place will become 2 only, because we divide here by x, so it becomes 2 over 1. So which is this? Now I can write this as lim x approaches 0 of 2, then 1 plus x squared over 3 factorial. Now if you substitute x equals 0, there you have 1 plus 0 squared over 3 factorial, which is equal 2 times 1, and it's 2. So that becomes the limits. All right. We will now look at another method of evaluating limits, known as the epsilon delta definition of limits. Now we are going to look at epsilon delta definition of limits. Let f of x be a function defined at every point in some open interval containing A, except possibly at A itself. The limits of f of x as x approaches A written mathematically as lim x approaches A, f of x equal L the limits of f of x as x approaches a is L, written mathematically as lim f of x as x approaches a equal L. If given epsilon greater than 0, there exists delta greater than 0, such that the absolute value of f of x minus L is less than epsilon, however small, whenever 0 is less than x minus e and less than delta. Right, so this one is called the epsilon delta definition of limit. Let f of x be a function defined at every point in some open interval I containing e, except possibly at a. That means f of x is defined at every point. It may not be defined at a, but that does not mean that you will not get the limits. Because from what we have seen, you see some places there, if you substitute the value directly, it's not defined. But we still have the limits. That is what this place is talking about. Now the limit of f of x as x approaches a is L, written mathematically as lim f of x as x approaches a equal L. If given epsilon greater than 0, there exists delta greater than 0, such that the absolute value of f of x minus L will be less than epsilon, however small, whenever 0 is less than absolute value of x minus e and less than delta. All right. These concepts, we are going to illustrate these concepts. We are going to illustrate these concepts using this function. Now consider this function. I want to show you what epsilon mean and what delta mean, so that we really get the proper understanding of this definition. We'll go back to the table where we consider this function. Consider the function f of x equal x squared plus 1, whose table is shown, whose values of x and f of x corresponding values of x and corresponding values of f of x, okay, whose values of x and corresponding values of f of x are shown below, are shown in this table below. So this is the table that we had before for x, and then we also have for f of x. So we want to consider it as x approaches 2, as x approaches 2. And from what we had last time, we see that I just want to start maybe from x approaches 2 from the left. This will be 1.5, 1.6, 1.7, 1.8, 1.9, 1.99, 1.999. All right. And we know that in this function, we have some corresponding value like 3.25. This is corresponding value for 1.5. Then 1.6 square plus 1 gave us 3.56. 1.7 square plus 1 give us 3.89. then 1.8 square plus 1, it was 4.24. 1.8 square plus 1 give us, okay, 4.24. Then 1 plus 1.9, 1.9 square plus 1 give us 4.61. 1.99 square plus 1 give us 4.9601. So 4.996001. Good. So here we want to see what this definition is saying, that if given epsilon, there exists delta such that the absolute value of f of x minus L is less than epsilon whenever absolute value of x minus a is less than delta. So here x approaches 2. This 2 is like saying a in this context, and then this one f of x approaches 5. So this 5 is L, that is the limit. Now if you go every place, we want to look at absolute value of f of x minus L less than epsilon. What does it mean? And another one is 0 less than absolute value of x minus a less than delta. What does it also mean? So we come here. For this one, it said, this place is saying that, see, this is for x minus a. Here, absolute value. Absolute value means it must be positive, cannot be negative. So if I say 1.5 minus 2 will give me 0.5. Then there is a corresponding value there too, which is 3.25 minus 5. Where? Which 5? This 5. This side is for f of x. So each one there, f of x minus L. If I say 3.5 minus 5, is the same thing with f of x minus L. I come here now, 3.56 minus 5 is f of x minus L. I come the next one. So the definition is saying that you will continue like that at each point. As you get f of x minus L, you also have corresponding one for x minus a. So here is 1.9, which is x, minus a, minus these two. You will come to this place where you have a small value. Look at this place. Let's look at here. 1.9999 or 1.999 minus 2 give us 0.001. Very small, 0.001. That's why we say, however small. Can we be able to find something like that here by saying 4? Look at 4.996001 minus 5, because L is 5. It would then give us 0.00, yes, 3999. So you see that if you take this in closer again, 1.999999 minus 2, you get small value. You can also get the corresponding value this place by saying 4.99666 or whatever minus 5. You get a small value. Those small values are what we call epsilon and delta. Now, the value of epsilon, the value of delta depend on epsilon. Example, proof using epsilon delta definition that 2x plus 1 as x approaches 4 equal 9. And look at that. So this is how we evaluate algebraically lim 2x plus 1 as x approaches 4 equal 9. So we want to prove whether it's true. So let epsilon greater than 0 be given. What I mean there is, let there be a small positive value. Let it be a positive value, however small. Let it be a positive value, however small. So that means even though it's very small, let it be. And I have shown you the value of epsilon. That is, when you minus f of x from L, it remains, there is a value there. As you take it closer down, 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 you see that you get the corresponding value at each point. But when you bring it down to where the limit is, it becomes very small. So let that small number be given. There will also exist delta greater than 0. That is, there will be a corresponding value from the table, what I have just demonstrated, such that the absolute value of f of x minus L will be less than epsilon whenever 0 is less than x minus e and less than delta. Good. So here we will have something like this, that 2x plus 1, that is the absolute value of f of x. So f of x is 2x plus 1. We put it there. Minus 9, because 9 is L, the limit, will be less than epsilon whenever 0 is less than x minus 4. You see, in this context, a in this context is what x is approaching, and here is 4. So we put the 4 here. It will be less than delta. So here we see that we have 2x minus 8 is less than epsilon whenever 0 is less than x minus 4 and less than delta. Look at that. So here I can write it like this: 2x minus 4, you see I factor out 2, will be less than epsilon whenever 0 is less than x minus 4 and less than delta. Now I come to where I have x minus 4 and x minus 4. If 9 is not the limit, we will not get to this place that we are. So since this is the same with this, it means there is, if given epsilon, there will be, because there is a corresponding delta. That is one of the facts. If I divide this through, I will have like this, that x minus 4 is less than epsilon over 2 whenever 0 is less than x minus 4 and less than delta. Now since look at this is equal this, like I have said, I will continue with that side to see that x minus 4 is less than delta. Now in a lecture on inequalities, we come to where we talk about inequalities involving absolute value, where we have that minus delta is less than x minus 4 and less than delta. This is how we can remove this absolute value. All right. Now I'm going to add 4 to both sides so that we'll get x. So adding 4 to both sides, we'll have 4 minus delta is less than x and less than delta plus 4. Okay, so I'm going to set delta less than equal 1. Of course, you know that from what I show you in the table, the value of delta is very small. So, and there's also a corresponding value of epsilon. Okay, so, but there is no how it will be bigger than 1. So we always set it to be like this, which means I can say minus 4 minus 1 less than x and less than 1 plus 4, which give me 3 is less than x and less than 5. Right, at this point, what happened is I will now compare delta to this, times it with this. It means I will have that 5 delta is equal epsilon over 2, which means delta is epsilon divided by 2 times 5, which is 10. So I've got the value of delta. The same way, epsilon is, look at here, epsilon is 10 delta. So this is how we make the proof. Now we'll take another example. Determine the number delta greater than 0 such that lim 2x plus 4 as x approaches 3 equal 10, given that epsilon equal 0.01. All right, so in this function now, we are asked to determine delta. That is a positive value. Delta greater than 0 means positive value. What we want to get must be positive. Okay, such that the limit of this function is equal to 10 if, or given that epsilon is 0.01. So, solution. Lim 2x plus 4 as x approaches 3 equal 10. Now, let epsilon greater than 0 be given. Now, there exists also delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than x minus 3 and less than delta. Look at that, x minus 3. Or let me state it first, that x minus a, so that you now see the position of a. Position of a here is 3. So that will imply that absolute value of 2x plus 4 minus 10, look at that, because here we have shown that the limit is 10. So minus 10 will be less than epsilon whenever 0 is less than x minus 3 and less than delta. See that? So here you then see that this will give us 2x minus 6, because 4 minus 10 is less than epsilon whenever 0 is less than x minus 3 and less than delta. All right, so here we see that we can factor out common thing here. So we have x minus 3 is less than epsilon whenever 0 is less than x minus 3 and less than delta. So you divide here, you have x minus 3 is less than epsilon over 2 whenever 0 is less than x minus 3 and less than delta. Notice that we come to a point where we have the same value again. So which implies that 0 is less than x minus 3 and less than delta. For minus delta is less than x minus 3 and less than delta. So if we add 3 to both sides, adding 3 to both sides, we have 3 minus delta is less than x and less than delta plus 3. Now set delta to be less than equal 1. We'll have 3 minus 1 is less than x and less than 1 plus 3, which gives me 2 less than x and less than 4. Now if you compare this at this point to delta, you can then see that 4 delta is equal epsilon over 2, which implies that delta is epsilon over 8. Alright, now since epsilon equals 0.001, it means that delta is 0.01 over 8. 0.01 over 8, which by evaluating it, that is 0.01 divided by 8 will give us 0.00125. All right, so we are able to find the value of delta when epsilon is 0.01. So let us take the next example. I'm going to prove that lim x squared as x approaches to equal 4 using epsilon delta definition. So lim x squared as x approaches 2 is 4. Now let epsilon greater than 0 be given. There exists delta greater than 0 such that the absolute value of f of x minus L will be less than epsilon whenever 0 is less than the absolute value of x minus e and less than delta. So here we have that f of x is x squared, L is 4, so less than epsilon whenever 0 is less than x minus 2 and less than delta. Now here we see this one is quadratic, that's power 2. Is different from what we were doing because those ones were linear function. So we can factor this. This is different of 2 squared. So we have x plus 2 less than epsilon whenever 0 is less than x minus 2 and less than delta. Now we come to see that we have something here and here of 1 which is common. So we constrain with 1, later we'll also deal with the other one. It means that minus delta is less than x minus 2 and less than delta. That is from what we have done before. I'm taking this one that is equal to 1. So adding 2 to both sides. Why do I add? So that these 2 will go. Then I will have 2 minus delta is less than x and less than delta plus 2. Now there is another one here. This is x plus 2. So I have to add the 2 again. I will have 2 plus 2 minus delta less than x and less than delta plus 2 plus 2. Which give me 4 minus delta is less than x and less than delta plus 4. Now I'm going to set delta less than equal 1 so that we'll have 4 minus 1 is less than x and less than 1 plus 4. This gives me 3 is less than x and less than 5. Now if I compare this with delta. I now have that 5 delta equal epsilon, which means that delta is epsilon over 5. We can also write this as the minimum of epsilon over 5 and 1. So this is how we can solve this side. It's very simple to solve. It's not a difficult task at all. All right, so now we'll move to another kind of limit that we talk about, limit at infinity. That is what we want to do now. Next, we look at limits at infinity. Given any independent variable, say x, if x increases without bound, through positive values, we write that x approaches positive infinity. Also, if x decreases without bound, we write that x approaches negative infinity. The following are true for limits at infinity. If R is any positive number, then number 1, limit as x approaches positive infinity of 1 over x raised to r will be equal 0. Now take note of this property, because that is what I'm going to explain this again during example, why we say this will be equal 0. I'm going to explain it. 2, the limit of 1 over r as x 1 raised to r as x approaches negative infinity will also be 0. All right. We'll take example and see the practical aspect of it. Example, evaluate lim s approaches positive infinity of 4 of x plus 4 over 3x squared minus 5. All right, see, for instance, this, we are going to evaluate it in this way. Notice that x is approaching infinity. It's not approaching a definite value. It does not have a particular value like other ones we are doing. So here we have the limiting value of x plus 4 over 3x squared minus 5 as x approaches infinity. So here we are going to divide the numerator and the denominator by the highest value of x, and that will give us s over x squared. You know, the highest power of x here is x squared. plus 4 over x squared over 3 x squared over x squared minus 5 over x squared. Now, the limit of this as x approaches infinity. And this will give us limit as x approaches positive infinity of, now this will be 1 over x, and this one is 4 over x squared, then 3, because this can cancel this, minus 5 over x squared. Now this gives us limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 4 over x squared over the limit as x approaches infinity of 3 minus the limit x approaches infinity of 5 over x squared. So, at this point, since x is approaching infinity, look at, like we have 1 over x. When x gets to, say, 10, you have 1 divided by 10. When x gets to 1,000, you have 1 divided by 1,000. Of course, it will be very small. When x gets to 1 million, 1 still divide 1 million. So it will be very, very small. And before you know it, it will converge at 0. So that is what this theorem was trying to say. So meaning that this here will have 0 here, plus the same thing happen here, 0 over, this is 3 minus 0. And this gives us 0 over 3, which is 0. So the limit there is 0. This is how we evaluate limits at infinity. That is limits where x approaches infinity. X does not approach a definite value. So you just divide it by the highest value of the independent variable. Could be t, could be x, or whatever. Then you simplify it and take the limit. We want to take another example. Evaluate lim x approaches negative infinity of 4x squared plus 4x cubed plus 2x squared minus 5 over 8x cubed plus x plus 2. So lim x approaches negative infinity of 4x cubed plus 2x squared minus 5 over 8x cubed plus x plus 2. So I'm going to divide through by x cubed. Why do I divide by x cubed? Because x cubed is the highest power of the independent variable x. So we have lim x approaches negative infinity of 4x cubed divided by x cubed plus 2x squared divided by x cubed minus 5 divided by x cubed over 8x cubed divided by x cubed plus x divided by x cubed plus 2 divided by x cubed. And then we will have something like this. Lim x approaches negative infinity of 4, because x cubed cancel x cubed, you have 4, plus 2 over x minus 5 over x cubed over 8 plus 1 over x squared plus 2 over x cubed. Then if we have that, we can then take the limit at each term as x approaches negative infinity of 4 plus limit as x approaches negative infinity of 2 over x minus limit as x approaches negative infinity of 5 over x cubed over the limit as s approaches negative infinity of 8, limit x approaches negative infinity of 1 over x squared plus limit x approaches negative infinity 2 over x cubed. Now, we see that this one will become 4 plus 0 minus 0. Why is it 0? Because when x approaches infinity, the value of 2 over x will be very small and converge to 0. Same thing will happen here. Then you have 8 plus 0 plus 0. That gives me 4 over 8, which is 1 over 2. So 1 over 2 is the limit as x approaches negative infinity. All right. So we'll look at another subtopic, and that will be continuity of function.